So, we have seen one major application area of microwave is radar. Let us now move on to another application area, which is cellular communication or cellular wireless communication. So, we briefly review some of the cellular system fundamentals. Cellular technology aims at achieving high system capacity with limited radio spectrum. Now, when it is a wired communication, if we lay cables or wires, we can transmit or reuse the same frequency in these cables without and increase the capacity of the system. When it comes to wireless communication, wireless is essentially a broadcast media. So, whenever we transmit in one particular frequency, if another transmission is there in the same frequency, there will be interference. And cellular technology aims at achieving high system capacity when you have limited number of frequencies. Cellular design makes the use of the fact that power of a transmitted signal fall off with distance. So, this is the characteristics of wireless transmission. As we move away from the transmitter, the signal strength reduces, and sufficiently away from the transmitter, the signal becomes very weak, and the same frequency now can be repeated. So, cellular system architecture intelligently exploits this feature to improve the overall capacity of the system, that means providing large number of channels while using only a limited set of frequencies. So, two users at spatially separated locations can operate on the same frequency with minimal interference between them. This is the objective, and this allows very efficient use of cellular spectrum, so that large number of users can be accommodated. So, spectrum or the frequency is a very scarce commodity, and we want to utilize this very effectively, so that a large number of users can be served. For example, if we consider the mobile communication scenario today, there are huge number of customers or users who are using these services, and these large number of users are essentially being supported only over a limited band of frequencies, and that is being possible because of the intelligent design of the cellular communication systems. So, cellular concept by itself is a system level idea which uses many low power transmitter called base stations, and each providing coverage to only a small portion of the total service area. So, if we want to serve a very large, geographically very large area, maybe some cities, some suburban areas, so it is covering the entire country. So, very small or low power transmitters called base stations, which provide coverage to a limited service area, and there are large number of such base stations are deployed to provide the overall coverage. So, in a city there may be hundreds of base stations which provide coverage in its individual areas. Each base station is assigned a portion of the total number of channels available to the entire system, and neighboring base stations are assigned different groups of channels. So, in this way allocation of channels are made, system capacity increases by reducing the frequency within the region of service. So, these are the concept based on which cellular communication technology was developed. Now, of course, over the years many other advanced features or characteristics have been used to improve the coverage, throughput, and also the quality of service. Now, when we have a group of cells which use the same set of frequencies are known as co-channel cells. The reuse of frequency may give rise to interference between the signals of these cells, and this is called co-channel interference if the power level of the transmitters as well as reuse distance are not properly designed. So, we require, for the purpose of analyzing the performance of cellular communication system, a regular cell shape, so that we can carry out systematic design. In principle, the cell boundaries or the periphery of the cell will not be having regular shape, it will be irregular because of many propagation effects. The signal in different directions will get attenuated to different degrees, and the coverage will be different even if the distance is same from the base station. So, for the purpose of systematic design, we consider a tessellating structure, a structure that can be repeated, and the geometric shapes which cover the entire region without overlap and with equal area, there may be several choices. So, the regular geometries like equilateral triangle, square, hexagon, these are the geometries which we can tessellate, and without any void we can cover the entire service area. For example, circle, if we do not overlap, then there will be void. So, among all these geometries, hexagon is the most preferred one, and its shape is closer to a circle also, but at the same time we can repeat hexagons and we can cover a geographical region without leaving any void. So, that is why in the design of the cellular communication system, Often cells are depicted as hexagons, although in reality the shape of the cell will be quite irregular. It will not be identical in all direction. There will be some places where the signal strength will be very low as compared to other places. But when we do the system design, representing cells with hexagonal geometries give lot of advantage, and that is why it is normally used. So, we show the cellular system with hexagonal cells. So, here we can see that we have covered one geographical region using hexagonal cells, and they do not leave any void in between. Now, in one of those cells we are showing a base station, and then we have a mobile station, and then between the base station and the mobile station the communication takes place using channels. So, usually a channel will represent by uplink and downlink frequencies, which will be different, and this type of channel is also called frequency division duplex or FDD. Now, the basic architecture is like this. We have a base station serving many mobile stations, just one is shown here as a representative quantity, and then this link from base station to mobile station or from mobile to base station, these are wireless. Then these base stations, they are connected to another mobile telephone switching office, and usually they are connected by very high speed lines such as optical fiber. Mobile switching stations have connection to PSTN or public switched telephone network, and also it is connected to the internet. So, in that way, although the mobile initially communicates with its base station, through base station and mobile switching office, it can get connected to public switch telephone network and also to internet. Here we explain the operation of the cellular system. So, suppose we have two cells and we have depicted this cell as overlapping regions here. Now, we have two base stations serving these two regions, and we have mobile stations in the service area of each base station. Now, we have downlink frequencies or channels through which the base station communicate with the mobile station, whereas we have uplink channels through which the mobile station communicate with the base station. And suppose this mobile is to communicate with the other mobile, it does not communicate directly all communications are routed through its base station. Now, this type of simultaneous communication between more than one user, these are called multiple access. So, multiple access may take place using various methodologies. The oldest one was frequency division multiple access. The GSM or the second generation telephone systems, mobile systems, they used TDMA, time division multiple access. Then next generations used CDMA or code division multiple access. So, in that way the resources may be shared by large group of users through the multiple access technology. Now, all these mobiles are attached to this base station, but because of the mobility, the mobiles may change the point of attachment as it moves. Now, at this location it gets a better signal from the nearer base station, and therefore, a connection is established with the second base station, whereas the earlier connection is snapped, and this is called handoff. So, the mobile stations which are located near the periphery of a cell, they undergo handoff many times, and the user should not experience that it is now being served by a second base station. So, it is very important to design the handover which is very smooth without interrupting ongoing communication which the mobile station might be carrying out with another mobile station. Now, wireless communication or wireless technology has become the buzzword because of several advantages. It allows to be stayed connected and provides mobility. It is anytime, anywhere, increased access to information when needed most, and remove the need of extensive cabling and patching, and it has produced a measurable impact on the return on investment. Last several decades have shown tremendous growth because of wireless networking is viewed as one of the technologies promising the greatest impact on productivity in different front. Now, this cellular communication system, they operate in the microwave frequency band, and we have seen several frequency bands. The most common bands are 800 megahertz, 900, 1800, 1900 megahertz. So, it depends, some amount of variation is there from region to region and different countries. Although wireless communication is very exciting, it is also technologically very challenging. The major challenge comes from the wireless media itself, and fading of signal is a very challenging issue. Then there are interferences, security issues are there, because when the informations are being transmitted over the air, it can be easily intercepted, and moreover the bandwidth constraint for multimedia communication. Over the years, the traffic pattern has also changed considerably. Initially, the cellular communication technologies were developed for delivering voice and text messages, but now the multimedia content in the form of images, videos along with voice and text, these are increasing, and once we go to this high resolution images or videos, the bandwidth requirement also increases. Now, achieving or providing large bandwidth or broadband access using wireless is a quite challenging task. Now, microwave frequencies used for cellular communication, they get affected by the propagation mechanism. Reflection takes place, there are refraction, diffraction and scattering effects, and because of this a signal transmitted from the transmitter appears at a receiver through different paths, and we call this multipath effect. Now, if for example these multipaths they appear with very little delay between them, but because of the random phase change they suffer, these signals at the receiver, these multipath signals, they may interfere constructively or destructively, giving lot of fluctuation in the received signal, and this causes the fading of the signal, and depending upon the medium through which these signals are propagating, this type of fading becomes very random. Now, one of the very basic equation that is important for modeling of these systems is the free space propagation freeze equation. So, suppose we have one antenna which transmits a power of Pt in the microwave frequency band, and suppose that this antenna is omnidirectional. In that case, it will radiate equally in all directions, and therefore, the power density will be, let us denote it by PDI, will be Pt by 4 pi r square watt per meter square at a distance of r from the antenna. Now, practical antennas will have some gain, that means they will radiate more in some particular direction as compared to the other. So, maximum of this gain function is called the gain and let GT denotes this gain. Then the power density PD, when we consider the antenna gain, will be PT GT by 4 pi r square, and this is the power density in the direction of maximum radiation. Now, suppose the receiver antenna is also aligned to pick up the signal from that direction, then the received power in the receiving antenna can be written as incident power density PD multiplied by A effective, where A effective is the effective aperture of the receiving antenna. For an antenna, the effective aperture AE effective and the gain of the receiving antenna, they are related as A effective is equal to GR, gain of the receiving antenna, into lambda square by 4 pi. And once we substitute this expression for the effective aperture, we get received power is equal to PT into GT into GR lambda by 4 pi r square. So, we notice two things here. As the distance from the transmitter increases, that means R increases, the received power decreases 1 by r square. So, it decreases very fast, and this is in fact the reason why the signal strength at a particular frequency will become very weak even in free space after traveling some distance, and the frequency reuse can be made beyond that distance. We also find that the received power, it varies as lambda square. Now, lambda is C by F, that means the received power will vary as 1 by F square. So, as we go to the higher and higher frequencies, our range reduces, because the received power achievable range, it reduces because of the decay of power with frequency. So, these were the considerations while choosing the frequency for the wireless cellular communication. It should provide sufficient range, and at the same time the frequency should be high enough so that the circuits have reasonable dimensions, because size of some of the circuitries in wireless systems, they are dependent on the operating wavelength. So, we discussed about free space, how the signal attenuates. So, in free space the received power attenuates as 1 by r square. With reflections and obstructions, signal can attenuate even more rapidly with distance, and the detailed modeling is quite complicated. Attenuation of signal strength due to power loss along distance travelled, we consider this effect which is known as shadowing. So, shadowing occurs because of the obstacles present in the path, and average large scale path loss for arbitrary transmitter receiver separation, this is denoted as PL bar D, that means average path loss is proportional to d by d naught raised to the power n. Here n is the path loss exponent and d naught is a reference distance usually close to the transmitting antenna, and it is in the far field of the transmitting antenna, with respect to which this path loss is specified, and therefore, in dB we can write average path loss at a distance d in dB is average path loss at d naught plus 10 n log d by d naught. So, once we have this path loss, the path loss expression what we have shown, this is a deterministic expression, and when this path loss is subtracted from the transmitted power, it gives us the received power at a distance. But by measurement, it has been found that at a distance d from the transmitter, suppose we have a transmitter and we consider a radial distance d. So, over this circle the path loss should be same in the ideal case, but in practical case through measurement it is found that the path loss is random and it distributes log normally about the mean distance dependent value. So, this is the path loss, mean path loss. On top of that, we add one quantity which is called x sigma, which is a zero mean Gaussian random variable with standard deviation sigma and also in dB. So, this part it gives the random change in the path loss when measured under different conditions at the same distance. And once we have this expression for the path loss, we can find out the received power in dBm, which is equal to transmitted power in dBm. dBm is with reference to 1 milliwatt. For example, 0 dBm represents 1 milliwatt, 30 dBm 1 watt, like that. So, when we have PT in dBm minus path loss at a distance d expressed in dB. This is very important to know this PR, because the design of the system, particularly the RF system in a cellular communication system, depends on what is the minimum received power with which the system would operate satisfactorily. Now, we said that when the propagation environment is different from free space, the path loss exponent n or path loss parameter, it changes. Usually wireless or mobile communication, they takes place in congested urban areas where there are lot of buildings, or in semi-urban areas where there are lot of vegetations. So, people have made extensive measurement, and from that measurements the different values of path loss exponent which are observed. So, in free space it is 2, urban area cellular it may be from 2.7 to 3.5 with lot of shadowing present, it may be as high as 3 to 5. In building LOS, here we can see that it is less than 2 because of some propagation effects. Obstructed in building, it may be as high as 4 to 6. Obstructed in factories, 2 to 3. So, different environment people have done lot of measurement campaign, and we have a good idea about what is expected to be the path loss in which range. Now, let us briefly touch upon the issue regarding co-channel interference. We have said that in cellular system frequency is reused at some distances. So, here these cells marked as A, they will have the same frequency. Now, a group of cells which actually divide the frequency among themselves is called a cluster, and the size of the cluster, the number of cells in a cluster is determined by n is equal to I square plus I j plus j square. For example, if we have I equal to 1, j equal to 0, then this cluster contains only one cell. If I is equal to 1, j is equal to 1, then it is a 3 cell cluster. If I equal to 2 and j equal to 0, then we have a 4 cell cluster. Similarly, if we have I equal to 2, j equal to 1, in that case we will have a 7 cell cluster which is shown here. So, these clusters can be having the number of cells satisfying this relation. Now, let us consider this cell. It is surrounded by 6 other co-channel cells, and whenever there is transmission in these cells, their transmission may affect a transmission within this central cell, and this interference effect will be most pronounced when the mobile is at the edge of the parent cell. That means, when its signal strength is likely to be very small or least from its own base station. So, in that worst case scenario, we can calculate roughly the signal to interference ratio that will be experienced by the mobile. So, signal to interference ratio S by I can be written as r to the power minus n. This is because of the power decreasing inside this cell, and assuming that the path loss exponent is same everywhere, for this interference power it is summation I equal to 1 to Ni di raised to the power minus n, where di is the distances d1, d2, d3 etc. from the base station of the location of the base station of the interfering cell to the location of the mobile. Now, when these distances are large compared to radius r of the cell, all these di's can be assumed to be equal to d, and therefore, this can be written as d by r raised to the power n divided by Ni. Ni is the number of interferers. For a hexagonal geometry, we find that this type of centrally located cell will have 6 interferers, and also for this type of hexagonal geometry, d by r can be shown to be equal to root 3 n. So, we can actually, for this type of cellular geometry, we can analytically estimate the expected signal to interference ratio that will be encountered at the edge of a cell, and this is the worst case scenario when the mobile is at the edge of this cell. Another important parameter is the Doppler shift, and it plays a crucial role, because when there is a relative movement between the transmitter and receiver, the frequency changes. Suppose we have a mobile user A, and this is the source S at an angle theta, and mobile is moving with a velocity v as shown towards the point B, and then theta dash is approximately equal to theta when this distance is less, and let it be delta x. then the difference from source to the mobile in terms of distance is delta x cos theta, and we know that a distance of lambda produces a phase shift of 2 pi. So, delta phi, the phase difference is 2 pi by lambda delta x cos theta. Now, Doppler shift f d can be written as 1 by 2 pi delta phi by delta t, if delta t is the time taken by the mobile to move from A to B, and this is same as 1 by lambda delta x by delta t cos theta, and when this delta t tends to 0, then dx by dt it becomes v. So, it is v by lambda cos theta. So, depending upon the angle between the source and the mobile and the operating frequency, and also based on the speed of the mobile v, it will experience different amount of Doppler shift. Many a time in cellular system design, the maximum Doppler shift that is experienced is very important, because it is related to one parameter of the channel called the coherence time, and for a time below the coherence time, the channel can be assumed to be steady, and it is assumed that after this time the channel experienced will be different. So, Doppler shift plays an important role in designing the signal processing algorithms in a cellular system. And at microwave frequencies, where lambda is very small, Doppler shift can be quite high. Without going much into the details of the cellular system, let us now quickly see some features of the mobile units. Please note that mobile in a wireless or cellular system is a transceiver, because there is two-way communication, and therefore it receives as well as it transmits. So, that is why we are talking of digital cell phone transceiver, and the RF unit, it is broadly divided. This is of course a older generation of second generation digital cell phone architecture, but it provides into the insight of how the different tasks are divided. So, we have the RF unit which operate in the microwave frequency, and then we have the baseband units, which these RF units are analog. Here we do a digital to analog conversion or analog to digital conversion, and these baseband systems, they operate at much lower frequency and usually employ digital signal processing. So, we have a antenna which is shared between the transmitter and the receiver chain through a switch or a diplexer. Now, while transmitting the signal from the microphone, it goes to the vocoder where it is encoded suitably, digital signal processing takes place, then it is converted in the analog form, and then we have frequency synthesizer which translates through this mixing process into an RF signal, and then it goes to a power amplifier and it is transmitted. While receiving, we have a low noise amplifier and then another level of mixer which actually brings it to some lower frequency, usually called intermediate frequencies or baseband frequencies, and then it is converted from analog to digital. While receiving mode, the signal goes through the LNA and then through a mixer which down converts the signal. It is converted from analog to digital, and then the processing is done using a digital signal processor, and then through vocoder it is given to the speaker. Now, there is an embedded controller which controls the different interfaces, and it is also linked to frequency synthesizer, digital signal processor. So, in a mobile phone we have display, keyboard, memory. So, it is a complex system out of which this part is the RF part, and we have already seen different principles of designing amplifiers, switches, etc. Wireless cellular technology, in terms of providing different services as well as technology wise, has changed very rapidly over the last few decades, and already 4th generation of wireless communication technologies have taken place, and we are looking towards 5th generation of such technology, and this has happened within last about 50 years. So, the first generation, it was primary service was to provide analog phone calls, and the key differentiator from the wire based system was that it introduced mobility. There were many issues, poor spectral efficiency, security issues, and it was analog in nature. Then the major change came as second generation, where digital phone calls and messaging, these were the primary services, and key differentiator was security, and this is the time where the mass adoption of mobile phone technology has taken place, but it has the limitation of data rate. Then 3G or third generation of phone calls again messaging and data, but better internet experience, and it offered broadband services, and there were a lot of expectation from both industry and users when 3G came into existence, but the real performance was below the expected performance. Then came the fourth generation of technologies, which is IP based services. Faster broadband, latency got reduced, and we are looking towards now the next generation 5G, which is expected to arrive in few years of time. And beyond 4G, and we are looking towards 5G, which is expected to arrive very shortly. And when we move from 4G to 5G wireless system, it is expected to provide instantaneous connectivity. Connectivity in heavily connected places, this is an issue where very large number of users are there. Many a time getting connection and maintaining connection becomes very difficult. Then this type of technology also will support direct device to device communication, and then massive machine communications, where we will have large scale deployment, where at both ends of the communication link we will have machines. Then moving networks, ultra dense network. So, these are some of the targets of the upcoming next generation 5G technologies, and ultra reliable communication. Now, the frequency band which we are using for wireless or cellular communication at this stage, all these are below 6 gigahertz, and already these bands are very congested, and therefore, next generation of wireless and cellular networks are anticipated to use higher carrier frequencies in the millimeter wave frequency bands, and technologies are being developed in the frequency bands around 28 gigahertz, in some cases around 60 gigahertz. So, as we move higher up in the frequencies, there are many technological challenges will come up. We have already discussed the range will get reduced, the fading, signal absorption, Doppler, these issues need to be addressed properly, and this will pose lot of challenge to the designers to come up with this type of next generation systems.